Swayam Prabha. Digital India. Educated India.
Okay, so let's continue. One of the problem is that when you're using these kind of simulations, at the interface you have a discontinuity. And because imagine to have in VOF 1, 1, 1, 1, 1, 0, 0, 0, 0, and then some other numbers. You are constructing the surface. But what is happening? That all the values related to the volume fraction are changing. So with the interface, for example, we are changing even the velocity. So we may have one velocity that is different with the other. And you know from what I said before, the velocity will be the same. Okay, so we have a jump in the normal velocity due to, for example, phase change. So the phase change is complicated in VOF or level set and so on because we have a jump not only in the mass, but not the mass, in the velocity, but also in the temperature, in the pressure, of course. So between liquid and vapor, of course, there is a jump in the pressure. So there is a jump in the temperature. So we need to work this because it's not really a big issue, but we need to deal in the proper way. Okay. So with the phase change, we have other, let's say, chances also. We can use an Euler-Lagrangian, so a DEM model with the phase change. Again, as I discussed just now, one way is to have several particles, several droplets, or let's say bubbles inside a parcel, so inside a digital bubble or a digital droplet. Okay. And this is interesting when we have large-scale processes. Heat exchangers, and so on, evaporators, condensers, and so on. For a DEM model, these are the equation of conservation, and let's speak about that because it's interesting. So again, we have the conservation of the mass, and already you see one change. When we have phase change, we need to add one term linked to the fact that we have a change in the component, as we have written when we deal with the multiphase flow, so in the theory. No? So if we have a phase change, we need to put one term that is linked to the fact that we have a liquid that is going to vapor or vice versa. Then we have another term, which is important, which is the momentum equation, which contains also the interface force between the continuous phase and the discrete parcels, so the force between them. But then, if we have phase change, we have also a force source coming from the phase change. In order to imagine that we have a droplet that is evaporating very fast. So we have a flow, so-called Stefan flow, from the droplet that is producing vapor that is going outside. Okay? But this is giving pressure because every time that we have a motion, there is a pressure. Right? So this is a force. And we need to include this force, which is related to the phase change. Then we have the other term linked to the phase, to the energy equation. And here we have, let's say, convection. Maybe we may have reaction between the two phases. We have radiation. And we have a heat source term that is linked to the phase change. Now, the problem is, as you can understand, is that when we have the Lagrangian solution, we need to write the equation of motion for the parcels. Okay? So the equation of motion is a classical Newton law for mechanics. And what is becoming very, very important is to understand which are the forces that are acting. Same thing for the angular momentum. If, for example, we have particles that are not spherical, they can move, so we may have, let's say, an angular momentum, as I said. So this is let's say, the Lagrangian, the Euler-Lagrangian simulation are very strong in this fact, because we can really have different situations also in terms of rotation. rotational velocity of the particles and so on. And then the same problem we have with the equation for the heating of the particles, or even boiling of the particles. So we need to write these terms in a way that we have at the end a good solution. And so you can understand that the point is really to understand how much are these terms, the forces here. One is the force exerted by the continuous phase, this one. This one is the force exerted by the continuous phase on the parcel. This is the non-contact force, because we may think that when we have the two parcels that are going close, they can merge, okay, in some case, or maybe they can repel each other. So we need to understand the different, for example, solid particles. If we have parcels of solid particles, and we may have a merge, but we may say, okay, no, there is no merge, they are going away. So we need to describe this kind of phenomenon. And then we have the contact force. So this is what I said now. So I said that. And then we have also the force that is linked to the phase change. So in order to describe where is the closure, where are the closure equations? Of course, the closure equations are here with this Fa, because the force that is felt by the continuous phase is the same force that is felt by the parcels. So we need to have the coupling. In the coupling is the secret, let's say, of the simulations. And so we have, for example, Fa in the continuum phase equation, the momentum conservation, is written again in terms of the forces that are acting on the parcels. And here we have the force linked to the parcels interaction. We have the buoyancy, for example. We have the Safman and Magnus force. The Safman force is a lift force. The Magnus force is a force that is related to the spinning of the droplets. If you have an example. If you have a ball, basketball, and you throw the basketball from a building, it's not going to go in this direction, but it's going to start rotating, and this rotation is going to change the motion. So it's going to, we can go to spiral. So this is the Magnum force. Okay. I'm saying because maybe you know, but I want to be sure. And what is also interesting is that there is a virtual mass force that is the force of the parcel together that are acting on the continuum. Because the fact that we have, let's say, the disparate flow is adding mass to the system, locally. And this is, of course, something that we need to consider, and we need to consider inside the so-called virtual mass force. The things are becoming really very complex because, for example, the contact force has a tangential and normal component, and then look at this. There are pages and pages of equations. So this is, I stop here, but only to understand it. And these are, can say, changing from one paper to another. So because, of course, everybody has ways to tweak the problem. So, for example, we can say that the normal component is a factor, Kn, and look at the equation for Kn and all the other equations here to describe what is happening. So it's becoming a little bit tricky. For example, these persons are putting 16/15. Okay, someone else, oh, I don't like 16/15, it's 1.2. Okay, good. Let's tweak this value. Okay. And so on. And of course, this can be really, it's only a no, I don't want to give any explanation of that. It's not my field. So Euler-Lagrangian is not my field, but I know the principle of these kind of simulations. But again, they are becoming very tricky because you need really to understand which is the coupling between one phase and the other. And so on. If you want to read more, there is this paper from 2023, because this is part of research now. It's not, I mean, one can think that it's consolidated and everybody knows how to deal with this, but it's still research. As I said, all these coupling forces, coupling energy, heat that is going from one phase to another is a question of tuning in many cases. So it depends on the material, for example, conductivity of the particles, and how can we deal with the conductivity of the parcels, because the parcel contains many particles, maybe with different conductivities, because we don't have only one solid particle, maybe we have different components of the solid particles, and it's becoming real. If you think to the applications, it's becoming really very complex, because you may have really, in the application where you have different components, different phases, we have reaction, chemical reactions. We may have Eulerian-Lagrangian model. Again, the same problem. Again, I'm not entering this, but it's interesting to know that we may have Eulerian model with phase change. And one can think, okay, it's complex. But I didn't speak about one thing. I didn't speak until now. Nobody said something. I was silent. About the turbulence. Because of what I said, now imagine how amplified it is when we are considering also the turbulence. Okay? Because until now, don't say anything. It's laminar flow. We didn't put anything about the Reynolds stresses and so on. But if you are adding also the turbulence, then it's becoming very complex. Okay? So, I didn't want to put only arg. So I said, okay. No, I mean, it's becoming too difficult, of course. I mean, it's even something that, okay, I should really study this in details, okay? It must be very honest. Because when I'm dealing, for example, with my droplet simulations, so on, turbulence is not, in my case, is not entering the, let's say, in the process so much, okay? When you have a droplet impact, you have vortices, you have all this kind of stuff, but really not the turbulence, okay? But my colleagues, for example, at the University of Wien, Alfredo Soldati and other people like that, they are dealing also with the turbulence. And okay, it's complex. And of course, when you are dealing, for example, with the sprays, and you're considering this turbulence in the sprays, imagine this is becoming really, really difficult. So you need to, now is really the frontier of research. So I need to stop because it's not for a basic course. And I'm not an expert because I'm not doing this for my research, okay? But this is becoming then something very, very complex. This is a paper that I found, and this is a three-fluid Eulerian approach for prediction of liquid jet atomization with turbulence. Wow, okay, everything together. So, in principle it's possible, but it's becoming very complex. Okay. Let's come back now, a little bit easier, the turbulence, okay? And we would like to understand how to deal with the VOF when we have a phase change, okay? So, what is happening? Okay, we wrote already, this is the expression of the VOF. And we have now the, as I said before, what is important is the Fs. In the VOF, we have a volumetric representation of the surface tension force. We may have different tools to do that. We have an interface sharpening, which is important to have a very sharp, nice interface. Everything is fine. One of the problems of the sharpening is coming or not? Yeah, it's coming. I didn't see. When you're doing, for example, air bubble rising on a pool, this is a box containing a liquid, okay? And we have a bubble rising. At the given point, we are going to have this bubble that instead of being very symmetric and going up, is going to dance. Now. Ding, ding. It's going to move. This is not happening, of course, in the reality. It should go up and stop. But this is a numerical problem. This is linked to the spurious current that you may have. So the droplet is now really dancing. So you will see that it's not going even to, let's say, to follow a trajectory that is going to the center, but is still moving a little bit. It's going, in this case, to the right. Next simulation is going to the left, because it depends really on the situation. And then you have the bubble that is going to the surface, and the surface moving. No, this is a classical case where we have a problem with the spurious velocity at the interface. And you can see, for example, in this image, that we have pressure fluctuations at the interface. And this is due to the fact that we are reconstructing the surface using a kind of approximation of the value of the volume fraction when we have a variation from 0 to 1 or from 1 to 0. Now, we need to avoid this. There are different ways to avoid. And for example, in open form, we have my interform, VOF, smooth variation, and so on. So we have different ways to do that. And in fact, the things are going to be better. And you can see here that the maximum velocity of the spurious currents, for example, in the case of the VOF smooth, is going really down a lot, while the common VOF is there is a problem with that. The pressure, the theory is the green one, and the capillary pressure is the red and the blue for the smooth and no smooth solutions. And as I said to you, level set is much better in this case. So the capillary pressure that you can get with the level set is good. Okay, we have a problem with the mass conservation, but also here with the VOF, if we are not paying attention, we have a problem with the mass conservation. So at the end they are similar, but for example, for the capillary pressure, we need to accept that the capillary pressure, the Laplace pressure, is not exactly what we would like to have. Okay, so there is a little bit of change. But of course, you need also to consider that the theory is a very sharp interface. And here the interface is not really, let's say, one cell. One can validate the open form, let's say, results, and they are very accurate. So this means that when you are dealing with, let's say, problem like droplets, bubbles, and so on, single droplet, single bubble, or a little bit more than single can be more. But the approximation is quite good at the moment. There are also codes that are not commercial, like the codes from other groups, let's say, around the world. Also, there is another code called Basilisk from Professor Stefan Zaleski in Paris, and a very good code for that. So we are able to simulate. For example, Stefan Zaleski did a very nice simulation, but also other people, let's say, not only him, of a spray when you can see all the structures of the liquid formation, the ligaments, and so on. Of course, you need a lot of computational power, but the physics there. Let me say that the physics there. So we can see the things. And now we can even do simulation from in the flow inside the nozzle to what is happening outside the nozzle. So we can do really a lot of work. So in this sense, now it's really interesting what we have here. You can see, for example, another problem of we have the gas that is entering in a channel. So we have a T-junction, and you can see that these are the images, and this is the VOF. These are the VOF simulation, and are very, very precise, very precise. One thing that is happening if you are not so precise with the simulation is that you may have always a little bit of gas, so it's difficult to have the right time for the breakup. Okay, so this is a test. These are, let's say, that usually the tests that we are doing when we would like to compare with the, let's say, with experiments. So this is the classical way. So the bubble rising, bubble rising on a pool, for example, the T-junction. Are really the normal tests for this, and droplet impact and so on. So this is a slide that I got yesterday from a student, Raul, that is working on this in this field, and this is what in open form is done about the reconstruction of the surface and the surface forces. And so you have different cases, and honestly, I mean. You need to choose the right one. So it's a combination of the advection schemes and the reconstruction schemes. And this is not, it's true that there is no general rule. So you need to really try really your best combination. You can try different cases. Also Raoul, for example, did this at the very beginning of his master degree thesis because we wanted to know which is, for our case, which could be the best combination of the advection and reconstruction. This is becoming a little bit too detailed for today, but only to tell you that what is happening. And so we can do many different simulations, also with the heat transfer. And this is, for example, the simulation of, no, this is not video, this is, okay. This is, for example, our simulation of, let's say, a bubble that is growing. Again, as I said, we need to patch a bubble in order to allow the bubble to grow and go away when we have a phase change, for example. Or in this case, for example, was not growing, was not a phase change still, but was, we have a hole and we inject air. The air is making so the bubble growing, and then the bubble is going away with breakup. So it's interesting because we are producing bubbles going like a Taylor flow inside the pipe. Now, what is happening again when the VOF is with the phase change? When we have the phase change, as we saw before, what is changing is the conservation of mass, that we have now a source term linked to the phase change. Can be liquid to vapor or vapor to liquid, can be condensation or evaporation. We have a surface term accounting for the surface tension as we did before, and we have a source accounting for the gravity. And here we have the source term representing the heat of evaporation, for example, okay? And we don't have here, we didn't put terms like the force linked to the phase change. Remember that there was a force linked to the phase change? No? We are not considering this. Honestly, someone tried to put, and there are codes where, even in open form, if you want, you can add this term. Some of my colleagues said, okay, I did, but there was no change, really. So otherwise, you should add one term that is a kind of pressure force linked to the fact that we have a phase change. But if a phase change is really not super fast, it should be okay. But in fact, in the general theory I did, so there was also a term to consider, but it's okay. In this case, it's not. And the big change is also with the phase transport equation, because we need to consider that we have a density variation in time due to the phase change. And the local and time variation of the density means that also the transport equation is changing the form. And we have now that we have a rho dot. If you think rho dot divided by rho multiplied by alpha is nothing else than alpha over t. So it's the variation in time of alpha. But due to the phase change, because we have a rho dot. Again, we have the bulk fluid properties, again, as an average with the volume fraction. When we have when we need to consider phase change and we have the energy equation, one of the very critical point is to understand how can we calculate the rate of evaporation, for example. We have a droplet that is evaporating, and we would like to know how much is the mass from the liquid to the vapor that is passing through the interface. So we can use, for example, this expression that is saying that, we have the temperature of the interface. Which is the temperature of the interface? Is the temperature of the cells where we have a value of alpha that is different from 0 to and 1. Okay, so imagine 0, 0, 0, 1, 1, 1, or vice versa. We have cells where we have something in between, and they have a temperature, because in all the volumes, open form is a finite volume method, so all the volumes we have a temperature. So this temperature is the interface temperature minus the saturation temperature. So we are not considering metastable conditions. This is another point. We are in equilibrium, metastable. We are considering the saturation temperature. We are not going inside the TS region of two-phase. Divided by what? Well, we can divide it by the latent heat, normal, latent heat is calculated at the saturation temperature, which is fine. And then we have a resistance. This is the major point, because how can we write the resistance? No? So this kind of interfacial heat resistance. So one way that is now accepted somehow is, I mean, we are playing with this. I'm not satisfied by this, but okay. There are, let's say, molecular simulation that are saying that this should be in this direction. This is coming from statistical physics, and we have this term that is the interfacial heat resistance that was proposed by Hart and Vondra in 2008. The point of this equation is that from the point of view the statistical physics is fine, this part, but then we have 2 minus a divided by 2a, and the authors are saying a is a value between 0 and 1, which is of course a big problem, because when it's 0 it's going to infinite, when it's 1 is going to 1 half, but which is the right value is a problem. And usually and here there is a debate. Someone is using 0.5 in the middle. We didn't have good results with 0.5. We use 0.9. I don't know if it's right or not, but we can play with this. Another point is that we are going to have these J. This is the, let's say, the value of the evaporation, for example, and how to conserve the mass, because we said that the COF has a problem with the mass conservation once you are constructing the interfaces. If we have a phase change, is even worse. Okay, so what we have done with Tassos, Anastasios Georgoulas, Dr. Georgoulas, this is our work in 2011, 2013, something like that. We use this method. So in fact, Weir law is due to this kind of smearing of sharp source term. So instead of reconstructing precisely the interface, before reconstructing the interface, we are allowing the surface having, let's say, the interface having a given dimension. Okay? So what is happening? It's happening that we are going to have, in fact, a value that is not precisely determined. So there is a gradient of alpha, okay? And we have a flow rate due to the phase change, because the evaporation is going from the liquid to the gas. So in this case, we are going to have at the end a kind of two interfaces at the end. We are going to have two interfaces. And the position of the right, let's say the real interface, is something between the two, okay? We don't know exactly which is the position. But now we have a degree of freedom, in the sense that if we are landing to have this condition, we can say, oh, the position of the interface will be the position to conserve the mass. So we are forcing the position of the interface in order to conserve the mass. Okay? It's working. It seems that it's working because, okay, we compare with many cases and it seems that it's working. But, okay, this is a way, okay? I think that it's not really our idea. We got from another paper before. There was something not really the same, but something similar, okay? So, but we are doing this. Of course, what is happening is that we are trying to understand where the alpha is a gradient, and so we are considering something between the liquid and vapor with a given accuracy. For example, we are putting 0.05 from one side to the other. So we are looking at when it's 0.05 and 0.95, in between there should be an interface, and we are dealing with these points in order to determine which is the right point to conserve the mass. A classical way to check if you did everything right is to compare the simulation of VOF simulation with a spherical bubble in a superheated liquid, no, in the GROW. So you have a superheated liquid, and you have a bubble inside. Of course, the bubble should grow. And we have even mathematical expression, so we know what is happening. There is an analytical solution, so from Scriven in 1959. There are other solutions, for example, from Prosperetti and so on. So there are, let's say, solutions of this problem that we can compare with. So it's fine. There are other people like Kunkelman and Professor Peter Stefan. Peter Stefan was here, let's say, only 1 week ago. And Mirko Magnini and many others. They did the same kind of comparison, okay? And this is not too bad. Again, the tuning parameter, there are two tuning parameters. One is less sensitive, is like alpha cut. So these points where we are doing this kind of mass conservation balance, but also A in the Harden-Wondra. In the Harden-Wondra, yes, we had 2 minus A divided by 2A. So we can deal with this, but we found that really, as I said, we can find the value, and we have that this is a very nice simulation. Pay attention that, for example, in this case, we have 1 micron cell size. 1 micron cell size. So it's very sensitive to the dimension of the. And why that? Because we need to solve the interface somehow. So you remember that I have a bigger interface, and we need to, let's say, to have the right position for the mass balance. No? In this case, if we have only 2 cells, we're going to do so much. Okay? So we need a little bit to have a little bit more, to allow more, having more cells in order to have a nice estimation of the position. This is the reason because we need to go 1 microns, 2 microns, 5 micron cells maximum at the, so computation is heavy, but it's quite accurate. It's very accurate, yes. And of course, if we have this kind of situation, we can build, for example, we can study flow boiling, even flow boiling. So we have a domain. This is a microchannel. There is a 200 it's written, sorry. 200 microns, 260 microns, 66 in the other direction, and is 1.4 millimeter long. One could extend. No problem to extend. It's only a question of computational time, so you need to wait. Okay. The cell size is 2 micron, and what I said before, when I saw some paper arriving with a cell size of, let's say, 100 microns or 50 microns, of course, they are trying to do that because their domain is bigger. Maybe there are, say, someone that is trying to do simulation of a microchannel boiling system, no? And the microchannel boiling system maybe is like that. It's 3 centimeters, like a CPU size. And for this is 1.4 millimeter, 1.4 millimeter. Imagine to have 30 millimeters. Okay, so in 30 millimeters, we can say, oh, but then it's becoming too long, because maybe you have, let's say, I don't know how many, but it's 30, it can be 1 billion cells. Oh, I cannot do it 2 microns. Let's do it 100 microns. Well, yes, you can, but then you're losing a lot of details, and your simulations are really bad. So it's a compromise. It's really a compromise. So in this case, you can work with that, so you can do something. And this is, for example, the formation of a bubble inside the channel, and then we have the bubble that is, there is a little bit of flow from the left to the right, and we are forming bubbles. The bubbles are growing, and then they are going in the flow. Of course, this is going to decelerate because of the drag, and so the other one is going to catch the first one. So we have this kind of situation where we have the classical generation of a slug flow, no? The Taylor, with Taylor bubbles inside. And you can see even what is important in this case, but I don't have time to treat this point, is the contact angle, the wetability, no? How to deal with the wetability. You can see at the end of this video that you can, the bubble is going against the wall, and the surface is deformed. Let me see. There should be somewhere. I think that here, somewhere here is touching the wall. Let me see. Oh. Yeah, this. So this is, is happening that is touching the word, is a strong deformation. So of course in this case we have a triple line, so we have, let's say, a contact angle problem, wetability. The wetability is inside the simulations, okay? So we have model for not only for the equilibrium contact angle, but also for the dynamic contact angle is included. And another point is that how can we generate the bubbles? We can put the bubbles. So you cannot see that, but we put, let's say, something like 5 or 6 micron bubble when we want. So it's not generated by fluctuations, thermal fluctuations, or something else. We put the bubbles and then it's growing. What do you mean? Of course, it's the interaction. Yeah. Of course, it's a visual. Oh yeah. The wake is there. Of course, I can understand. Yes, the continuous phase, both phases are with viscosity. Yeah, there is no turbulence. I don't want to touch this. I'm very scared. So no. But the viscosity is there. Yes, because there is a. I didn't put, but if you can see the velocity, you see really the velocity of the wake, the vortexes, and so on. This is included. 100%. Also inside, Also inside the bubble, you can see eventually the circulation, especially when you have a contact, you have the circulation inside of the vapor and so on. So this is included. They are viscous simulations. And so we can have different cases and so on, and so this is the situation, yeah. Okay. So as I said, I put at the end, we have the list of the books that you may read on this topic. I cited the books that I cited during these 4 days, okay? And all of them, I think. Yes, I also finished it. No, I didn't cite this one. No, there was something to say. It's a book that I published in 2022 with Joël de Koninck, the surface wettability effect. So we explore the surface wettability effects on phase change. When a phase change is happening, then we have a different wettabilities, what is possible to say, which is the effect of the wettability, and so on. Then we have the papers, the list of papers that we explore in these 4 days. It's a very long list. This is a list of important papers in multi-phase flows, and I think that is a very long list also in this case. And then we have my paper. This is a list of papers related to the Gian course. So this is the list of the papers I published in the last, let's say, 10 years. Not before, but I think that is giving you an idea of the work. And yes. And see, for example, in 2024, I work with a group, and then from the title you can understand, multiple emulsions, a new level set based on 2- and 3-dimensional simulation of multiphase immiscible flows for droplet formation. This is the last work I did on level set, and it's research. It's really research. So what I'm saying now is really, and this is emulsion. Emulsion are a particular situation where you have the interface that is changing because of the surface tension is changing with the position. So it's a complex, but this is becoming research. So in fact, it's published, let's say. Okay, and yeah, and then for example, the last this one with Chakraborty and Georgoulas and so on, we published in 2024, and this is also about the multi-scale modeling of boiling heat transfer. No? So we are doing, for example, we are trying to understand with the VOF, not with the level set, with the VOF, what is happening at the sub-micron scales. So because we arrive at 2 microns, 1 micron, what is happening when we are going to 500 nanometers or 100 nanometers, okay? Is the VOF able to capture the physics? The answer now in the next paper that we are writing now is that the answer is no. Because what you saw is that in my equation, the divergence of the velocity is equal to 0, so incompressible flows, okay? But when you're going down with the scales, if you're not considering the variation of the density, you may have a problem. This is when we compare our code, VOF code, with the phase field model. So when we are lowering the compressibility, then the two simulations are not going say to match anymore. So this is a problem. But let's say micro simulation and so on, I think that is not a problem. So finish. I anticipate to me. Okay. This is the end. Of course, again, I think that we are now giving the diploma, the certificates, and then I'm staying here again, but at 1 p.m. we have the oral exam for the 2 students that would like to get the credits. So I hope that you enjoyed. Please give me a feedback. It's very important because it's the first time that I'm doing the Gian, and it's the first time that I'm compressing 60 hours in 15 hours. I don't know, because I couldn't enter in the details, but I hope to have given you a kind of overlook of the topic, complete overlook of the topic. And I didn't know what the audience was. This was also maybe the first day could I have even, let's say, without the first day, then it was difficult because something was important. Maybe I could have deleted the part about thermodynamics, maybe this was too much. But about phase change and Navier-Stokes equation was better to say something. But maybe for the first 1 hour, I could have deleted 1 hour and put something more, let's say, on the modeling. Not something more, but I could have been a little bit slower, which was a little bit different. So without the thermodynamics, next time I can delete 1 hour on Monday, and I can be slower for the multiphase flow modeling the next day. But okay, but I like really to receive your feedback, and now certificates, right? Thank you so much.